So we are on section 3. So we have done our intro, we have done our Gaussian elimination. We should all be very, very familiar with row echelon and reduced row echelon, all that kind of good stuff. Now we're actually going to get into different matrix operations. So here's where we start to actually manipulate things. So I think it's pretty obvious that matrices are basically rectangular arrays of real numbers. We're going to be using matrices for many different types of projects. You're going to see this in your other courses. You're going to use it to represent all different types of information. Next week, we might even play with some applications. Next week, I'm going to tell you about some extra credit opportunities because I want you guys to see how linear algebra actually invades so many aspects of your lives that you don't even realize. So it's in all aspects of engineering, whether or not you have seen it before. But certainly, like, we can have things represented by matrices even in your own life. If you wanted to look at your different subjects and the days of the week and how many hours you spent, you know, studying for each of these, you could actually make some manipulations there if you wanted to. So we'll see about doing that later. So keep in mind, matrix is going to be a rectangular array of numbers. The other thing that you want to know for definition-wise, when you have the numbers that are in your matrix, those are going to be what we call entries. So here's where you're going to start wanting to keep track of your terminology. So here's definite examples of matrices. We've worked with some very simple ones. Just realize that they can include the irrational numbers as well. So, you know, in further chapters, you might have matrices that are a little more complicated. The other thing that you want to immediately know, this is going to come into play later on, so this is really, really important. We need to be able to tell people what is the size of our matrix, because that's going to tell us what we can and can't do with these matrices. So here, when you're talking about the size of the matrix, you're always going to tell it in terms of the number of rows first, and then the number of columns. So here, if you notice this particular matrix, it has 3 rows, it has 2 columns. Therefore, it's going to be a 3 by 2 matrix. Yes, go ahead.
That's actually a question.
Ah.
I thought we go by columns and rows.
No, it's going to be rows and then columns. So it's going to be really important. So what is it first? Rows, then columns. You're going to need to remember that because otherwise you're going to get really messed up on some of these problems. Okay, so let's just go ahead and try some of these together. What would this first one be? This first one here? Yeah, it's a 1 by 4, right? You got 1 row, 4 columns. What about this next one? What's something else you notice about that? You have 3 by 3. What do you notice? Got the same number of rows as columns, right? Keep that in mind. This next one, what would this one be? 2 by 1. And then what's this other one? That's gonna be a 1 by 1. Okay, so keep that in mind. Rows, then columns. So something that I do want you to know also is if you happen to have a matrix that looks like this, where it only has 1 row, that is going to be called a row vector or a row matrix. So this one has only 1 row. That's something else you want to know. This one, the 1, 3, this is going to be, since it only has the 1 column, it's going to be a column vector or a column matrix. And then this one, since it only has a single entry, it is both a row and column vector. So keep that in mind. Here's more definitions. Sorry, we got to get them out of the way, but this is how it's done. So the capital letters, you're going to see capital letters to represent your matrices. So this is going to be important because when you're writing out proofs, or if you're writing out different equations where you're trying to represent matrices, you're going to want to make sure you're using the language that everybody's going to understand. So your capital letters are going to be your matrices. Then your lowercase letters, those are going to be your numerical quantities that are going to be inside your matrix. So here you see A, B, C, D, E, F. Those are going to be your entries. A lot of times they're also called scalars. So keep that in mind. So we got big uppercase letters for matrices, lowercase letters for our entries or scalars. So here's some other notation that you're going to want to look at. So we've seen this before where if you have many entries, a lot of times they'll use like the same letter here. And then they'll have the subscript for like what entry it is, what row and what column it's in. Here's some other notations that you might have. So big A for your matrix is going to, here they might represent it like this, where it's a matrix of all your entries A with subscripts IJ, and then they're telling you the size of the matrix. If size is not important, then it's just going to be abbreviated this simply. Here's another way. If you're looking at a very specific entry in a matrix, you're going to have your big A in parentheses, and you're going to note which position it is, and then it's also indicated by its lowercase letter. So just make sure you're aware of these different notation types. So you'll see those again. So just to kind of reiterate this, so we have our big A, that's our matrix represented by these entries. So here we would be representing a specific entry by putting parentheses around the A, denoting the subscript. So if I said A11, what would that be? What entry would that be? Yeah, it's gonna be 2. What about A12? That's gonna be your -3. We've got our 7 and then our 0. So you might see notation such as this. Here, this is another thing I just wanted to go over. If you happen to see a lowercase letter that is bolded, so that means that you either have a row or column vector. You could also call it a row or column matrix. So usual matrices are going to be represented by a large letter or uppercase letter. However, if you happen to have the situation where it's a row or column vector or a row or column matrice, then it's going to have a boldface lowercase letter. These we don't really need to have the double subscripting, as we know that there's either one row or one column. Here is another thing that we're going to want to take note of. So here is going to be another definition is you want to know what is your main diagonal. Now, here it's going to be all along here, the diagonal going from the top left going down to your bottom right. Is there anything that you happen to notice about this? Do all matrices have a main diagonal? So which type of matrices do?
Same amount of column and rows.
Exactly, good job. So keep in mind, this is going to be particular to square matrices. And so they are going to be of the order n. So that means that they are going to be an n by n matrix. So that might be a good true false question. I might say, do all matrices have a main diagonal? You would say false. So that's another definition. All right. Then this is another really, really important one. Two matrices, this is our definition 2, two matrices are defined to be equal if they have the same size and their corresponding entries are equal. I think this is pretty self-explanatory, right? They're exactly the same size, all the entries inside are the same, you would say those matrices are equal. So here we're looking at matrix A. Yes, so Brendan, exactly right. Brendan, yes, with the main diagonal, yes, it would have to be square, same n by n, exactly. So here with the equality of matrices, we can see that A equals B when X equals 5. Under those conditions, those two matrices, A would equal B. If X happens to be something else, obviously those matrices are not equal. Why are A and C not equal? Yes.
Different dimensions.
Yep, different dimensions. So it's not possible for A and C to be equal. All right, so here is our first operation. They're simple at first. Don't worry, in following sections, things are going to get more complicated. So do appreciate how simple things are right now, because they are going to get more complicated. Yes. Let's go back. So
I just like that as B, like for example, X is like 5.
yes.
And for the B, can I switch the column all the rows so and they still be 4? Or like
No.
it has to be exact?
Has to be exactly the same. Otherwise, they are not equal anymore. So that's a good point. So the entries have to be the same in the same positions. Otherwise, they are not equal. Let's see here. So your first operation is whether or not you want to add or subtract matrices. Can anybody guess what might be important if we are going to add or subtract matrices? What do you think we might need to have happen? Yeah, they're gonna be the same size. So if you're gonna have basic operations like addition or subtraction, guess what? Those matrices have to be the same size. So that's gonna be a really important part. So here it says it right here in the beginning of this definition. If A and B are matrices of the same size, then you can add them up. Then you can subtract them. So to do this, all you're doing is you're subtracting the entries, or you're adding the entries of A and B. They're very easily added, or either that, or you're subtracting the entries of B from A. And so we're going to see what that looks like. So here, if we wanted to, can we add or subtract any of these? So which ones can we add or subtract? A and B. What about B and C? So I have on here that if we added or subtracted A and B, that would be defined. You would get a defined answer. If you're looking at B and C and you saw that they were different sizes, you'd say nope. And that would mean that it would be undefined. So you're going to want to know defined versus undefined. So in order to add or subtract this, so if we wanted to do A plus B, all you got to do is add the entries of A and B. And you have to keep them though in the same position. So what you would do is you would add for this position 1, 1, you would add 2 plus -4. So what would that be? So that's going to be -2. And you would do that for every single entry. You just add the two of those together. So the next we'd have 1 plus 3, that would be 4. Then we'd have 0 plus 5, that would be 5. We got 3 plus 1, that'd be 4. Go ahead and keep going like that. We'd have 1 here, so -1 plus 2. Then we have 0 plus 2, that'd be 2. Then we'd have 2 plus 0, that would be 2. Then we'd have 4 plus -1, that'd be 3. Then here we've got 7. Then we've got, we got a 0. Then we got 7 plus -4 is going to be 3. And then we got 0 plus 5, that would be 5. So where we're coming with that, very simple procedure here. You would do the same exact thing for A minus B. So here we'll just do the first row because I'm sure you'll get the gist here. Here we'd have 2 minus -4. So we have 6. Then we have 1 minus 3. We'd have what, -2. Then we have 0 minus 5. We'd have -5. And then we'd have 3 minus 1. That would be 2. So very, very simple. The only reason we can do that is because they are the same size. But you have to do the addition and subtraction for the very same entry position. So you're looking at this number and this number for your operation to go into this position here. So not too bad, pretty simple. Yes.
Can you go over the defined versus undefined?
Yeah, so defined means that we can do it. We can add or we can subtract because guess what? They are the same size. It's undefined. So an undefined addition or subtraction would be if you tried to add or subtract B and C together. We can't do it. We'd be like, I don't know what to tell you. They're not the same size. So that's good to know. You're going to want to recognize undefined or defined. Here we've got, now we've got a product. So here, if A is any matrix and C is any scalar, then the product CA is going to be obtained by multiplying each entry of the matrix A by C. So then matrix CA is said to be a scalar multiple of A. So I think that that's pretty self-explanatory as well. And so here's how you would make this notation here. So here, if we did scalar multiples, what would 2A be?
4, 6,
We got 4, 6, 8, 2, 6, 2. What do we got with this one?
0, -2.
That's 5. This one, we got what?
3, -2.
1,
Yep.
1, 0, and 4.
Yeah. So all you're doing is multiplying this scalar times each entry in your matrix in order to get your new entry. So not too bad. Easy enough. Let's see, we got a question online. Are you able to modify a matrix size by adding zeros to make it the same size? No. So why would that be no?
You'd be adding a variable.
Yeah, you'd be changing your entire system because remember our matrices came from a set of linear systems. So that would be saying, oh, we're just going to throw another line or plane that we're going to consider. And that might not be the case. So at this point, no, we don't want to just add whatever we want to make them the same size. That's a great question. Let's see, do they have to be the same? Yes, so you need to have matrices be of the same size in order to be able to add or subtract them. Okay, so here we're starting to get into products here. So I just wanted to show you, so here's where you're gonna have to kind of keep this straight in your head. So they want to know, okay, so A is gonna be an M bar matrix and B is gonna be an R by N matrix. Then the product AB is the M by N matrix whose entries are determined as follows. So here, to find an entry in row I and column J of AB, you are going to multiply the corresponding entries from the row and column together and then add them up into the resulting products. So you're probably like thinking, what in the world does that mean? So here, we are trying to figure out what is going to be the entry in the second row and the third column. What would that single entry be? So what they're telling you that you're going to be doing is you're going to take this row going across and you're going to multiply it by this column going down. So you're basically going to be doing 2 times 4 plus 6 times 3 plus 0 times 5. And what is that going to give you? So here you did the 2 times the 4, then you're adding the 6 plus the times the 3, and then you're adding the 0 times the 5. So you see how you're taking this row and then multiplying it by these numbers going down. So what does that give you? Yeah, so it's going to be 26. So you were doing the second row and the third column. So that means out of this matrix, you would have all these different points here. And so you'd be finding this entry in particular by adding, multiplying and adding all that stuff up. Oh, did I put 20? I'm sorry. Thank you. 26. So we'll be visiting that again later. Does everybody see where those numbers came from?
Yeah, but why do we in particular use second row and second column?
That way they're just doing arbitrarily for that example. So they're just saying, hey, you wanted to find what's going to happen in this particular entry spot in, and that's how you would add, that's how you would multiply and add all those numbers up to find that specific entry. So they're introducing you to this particular operation. So here we go. It says determine the entry in row 1 in column A. So what would this one be? What would we need to multiply and add together? They want to know what is going to be this spot right here. It would go in this spot right here because it's row 1, column 4. But how would we find that particular entry number? Yeah, so we got 1 times 3 plus what? 2 times what? 2 times what? 1 plus 4 times 2. So what would that give us? 3, was it 3 plus 5 plus 8? 13. So in whatever that new matrix is going to be, that spot right there, that'll be a 13 there. Does everybody see that? Okay. Let's see. No, Brendan, so we're still doing, we're looking through the examples in the chapters. I'll let you know when we're going to do problems. So the examples that are in your sections, those are never going to be your participation problems because we're always going to do problems at the end of the chapter, right? For your participation. So here is where this is going to be really, really important for multiplication of matrices and be able to find your different entries. You're going to need to think to yourself, is that do the number of columns of the first factor A, are they the same as the number of rows of the second factor B in order to form this product AB? So you're going to have to think to yourself, is this true or not? And if it's not, then it's going to be undefined. So you're probably wondering, what in the heck are you talking about? What does this even mean? So here is the trick. If you want to know if you can multiply 2 matrices together, here is the trick. Here you might have a matrix A. We've got a matrix B. We want to know, is their product defined or not? So remember before we were doing addition, subtraction. Now this is multiplication. So now you need to be able to tell, is multiplication going to be defined or not? So here's the trick. You want to write out what is the size of those matrices, and you're going to want to look for these things. You're going to want to look for whether the inside numbers are the same. If they're the same, then you can actually define that product. So that's the trick. So this M is going to tell you what number for matrix A? It's going to tell you number of rows. R is going to tell you what? Number of columns. And then for B, R is going to be telling you what? Number of rows, and then N is going to be the number of columns for matrix B. So you got to look to see if those inside numbers are the same, and then you'll be able to say, you know what? Yes, they are. And then the product, so to know whether it's defined or not, you're going to look and see if those inside numbers are the same. If they are, the product's going to be defined, and then you're going to ask yourself, well, what in the world is going to be the size of the product? Well, the cool thing is you take the outside numbers, and that's going to be the dimensions of your product. So does everybody kind of see that? Okay, so we'll look at a problem really quick. So here, example 6, let's look at A and B. Is that going to be defined? Ooh, yes, it is. Because looky here. These 2 numbers are the same. It means it's going to be defined. Then what's its size going to be? Yeah, it's going to be a 3 by 7 here. Okay, what about B and C? Yeah, so we're going to say this one. So we want to make sure we're using the correct words. This is defined. So BC, inside numbers are the same. Outside numbers, that's going to tell us our size. We got 4 by 3. All right, what about AC? Yeah. AC, here we got 4 and 7. Oop, nope. 3 and 3, don't care. So this one's going to be undefined. BA. Okay, we got some undefined. Why would you guys say undefined? Ooh. Yeah. You raise a very important point. In multiplication, order is everything. Okay? So here you would need to write it in order of the multiplication that you're trying to achieve. So here you would do your 4 by 7 for B, and then you'd look at your A, which would be 3 by 4. You'd look at these two numbers and you'd say, nope, can't do it. So this one would be undefined. So just think to yourself, order. Make sure that you check that out. Okay, so CB, what do we got for CB? That one's going to be undefined, yep. What about CA? Yep, it's going to be 7 by 4, right? Do you guys see that? So here we have C, we've got a 7 by 3, and then we've got A, which is a 3 by 4. These are the same, so it's defined, and then we got our dimensions are going to be 7 by 4. So this one is defined. So you're going to want to be able to do these really, really quickly in your head.
So you always go by the last number, or like when you put 7 by 4, you don't use when you use the 7, the first one.
Which one are you referring to? This last one? Yeah, so CA, you have to put the matrices in the order of this operation. So see how the order is CA? So I'm listing C first, then A. I'm looking at the inside numbers. These are the same, so it tells me yes. I'm gonna put a check mark. Yes, it's defined. And then your outer numbers are gonna tell you the dimensions. So you always put this one first since it's listed first. And then the 4 is gonna go second. So your matrix is gonna be a 7 by 4 resulting. Is that?
Yes.
Yeah. Okay, so this is what is, so the method that I just showed you before, where you go over a row and then you multiply each of those entries in the row by each of the entries of the column, and then you add them all up. This is going to be called your row column rule. So that's something you're going to want to remember. So that's one way to multiply your matrices. Okay. There's more than one way you can do it. This one happens to be the row column. So you're going over a row, taking all those entries, you're multiplying them by the entries of your column going down, you're adding up all those sums, and then you're going to get each entry in your matrix. So let's see. All right, so we are going to come back to that in a second. Something that we also want to bring up in this chapter that's important is that you can actually partition your matrices. That's going to be something that we're going to be manipulating in the future. We're not going to do a lot in this section, but it's introducing the idea. So you can so there's all kinds of things we're going to be doing with these matrices. So just realize here you've got a matrix. It can actually be partitioned here. And here you actually have different matrices that's being partitioned into. And as you notice, each of them will be denoted, there's 4 different ones. So each one within that larger A matrix. So this one would be A11, it's for this one. This A12 is going to be for that matrice. This one's going to be for this submatrix, and that one's going to be for that submatrix. So you'll notice that it's also interesting that you can get different types of matrices when you partition like this. So this one's a pretty large matrix. This one happens to be a row matrix. Here you're getting a column matrix out of it. Here you're getting both the row and column with that single entry. So there's going to be lots of different ways we're going to manipulate things. So just realize that. Here's another way that you could partition it if it becomes useful. Here you can choose to have all of your matrices be row matrices. So see how they've, this row would then be R1 submatrix, and see how it's bolded? Because these are row matrices. So don't forget, row matrices or column matrices always have that bolded lowercase letter. So then this partitioned would be this R2. This one would be here. And then this itself would be forming a column matrix. So lots of different stuff. Same with column. You could choose to do it that way. You can create, partition it so that you have different column matrices. The other thing that this section wants to bring up is that we're going to be making more and more connections between matrices and linear combinations. So you can, yes, go ahead.
What would be an example of partitioning being used for, like, what would be an example being used for partitioning?
Yeah, if for instance, some information indicates one thing, other information indicates something else, it would depend on like what you're using those numbers of the matrix for. Like we saw in like that other example, you might have split things up into subjects versus days of the week, but then maybe you want to partition some of them because maybe days of the week, some of them are weekend. You know, like there's going to be different reasons why you might want to partition things, right? Yes.
Would I then be able to do like operations on like that partition.
Yeah, so you might do operations only on that partition, and then that might affect things. So a lot of that's more advanced for later, but just kind of keep that in mind, that you're gonna be able to use matrices for a lot of different things. Let's see, so for instance, oh yes, so like I said, the other thing to keep in mind, because as we go through these sections, you're gonna want to start having the light bulbs go off, is that matrix products can also be described as linear combinations. So just to kind of show you here, if we have a matrix A and we have a column vector X, well, that product, we could describe it as here, this combined one, AX, or if you wanted to think about it, you could almost think of it as a linear combination here. So we are taking each entry of X, and it now becomes the coefficient for the columns of A. So we're going to be doing manipulations like this, where they're going to resemble linear combinations with our matrices. So here, these entries of X would actually be the coefficients to these column vectors of A. So just keep that in mind as well. I'm not going to do anything too much with it this section, but it's going to come up again. Here we also, so here, yeah, this would be an example here where you could actually go ahead and multiply that out. So how, if we're going to do a linear combination, and these were our coefficients, what would that look like? So I'll show you that other slide again. So here you're taking this column vector. These entries are now becoming the coefficients that you multiply. Here you could be breaking these down. So this 2 could be times this first column vector here. Minus 1 times 3, 2, 1. And then plus 3 times 2, negative 3, negative 2. And as you will notice, you'll get an answer as well. So this kind of resembles the format of linear combinations, correct? Does everybody kind of see that? So we will be revisiting that. So you just want to look at that section briefly, but we'll be doing problems in later sections that are going to make that more clear. So we will go ahead and look at this one. Okay, so now, remember before I had showed you the row column multiplication? So here we had gone, taken a row and then multiplied it down a column to get that first entry here. Well, now we're going to do the reverse. Well, not necessarily reverse, but we're going to do the multiplication instead by column row expansion. So here, so this will be a different way to do it. So the first one I showed you was row column. Now here is going to be column row. So here you've got your columns of A. We've got 1, 2, and then we got the next column is 3, negative 1. Then we've got the row vectors of B here. So I'm going to go ahead and put A here. This is B. Keep in mind, order is going to matter. So this is going to work here. So here we got the row vectors of B. That's going to be the row 1 is going to be 2, 0, 4. We got row 2 is negative 3, 5, 1. So what do you think we're going to do with that? So if we do column row expansions, what do you think we might do? Anybody have idea from the reading? Anybody want to take a guess? So before we did row column, now we're doing column row. Kind of broken it up there just so you can see what's what. So if you look at the next slide, this would be the column row expansion. So here's the first column of A times the first row of B. Here we have the second column of A times the second column of B. So here that is going to be how you are going to go ahead and you're going to multiply this and then you're going to add it together. So here we've got 1, 2 times this 2. That's going to give us 2, 4 for those entries. And these are both going to be 0. Then we do the 1, 2 times the 4. That's going to give us 4, 8. Then we're going to go ahead and do this column times each of the row entries. So this one is going to be lead to negative 9, 3. Then we got 3 and negative 1 times this 5, which is going to lead to 15 and negative 5. And then we got 3 times negative 1 is going to be times this 1. So we're going to get 3, negative 1. So then once we get those, what are we going to do? We're going to add them both together. So that is going to be what is going to be our column row expansion. So a little bit different methodology there. So once we get to this point, what do we know we can do? Yes. Yeah.
So in column row expansion,
Mhm.
to me it looks like you're just taking scalars and multiplying it by the column matrix.
Yes, you're taking this this column and you're multiplying it by each of these entries in the row of B.
How's that compared to column?
Yeah, so row column, here we were taking this row and multiplying down and adding them. So here that would be 1 times 2 plus 3 times the -3. So what would that give you? 2 plus -9? Was that -7 for that first entry? Then you do it again, 1 in the 3 times the next column down. So that'd be 0 plus 3 times 5. What would that be? Be 15? Then you do it again. So see how you're doing the row, then going times the column down? This way, you're taking the column and then multiplying it across those row entries.
Okay.
So it's a little bit different order of things. So one's doing row column, the other one is doing column row. See how you got a little slightly different numbers there? You won't get those same numbers until you add both of these up together. Yes.
So for column row expansion, all we're doing is we're breaking down like two matrices into their column.
Then rows. Yeah. And then adding those two resulting matrices together. So this one, you're going to get two different matrices that you're going to add together. This one here, you're doing row, column, you're getting that entry. You're doing row, column, getting this entry. You're doing this row times this column, getting that entry. Then you're going again with the second row. You're doing this second row times these two, adding them up. 2, -1 times this second column, putting it in. 2, -1 times these over here, putting it in. And so you don't end up with two different matrices. You're kind of doing it all in one step.
And you will end up with the same matrix in the end, though.
Yeah, exactly. So
The row column is one step and column row is 2 steps.
yeah, so this one you could get all of your entries that you need. So here we got, what's the next one here? So 1, 3 times this 4 and 1. So here this would be 4 plus 3, that'd be another 7, right? Let's go ahead and do the next one. So here I'm doing 2, -1, this row, and then I'm going to do it times this column going down. So I've got 2 times 2, that's 4, plus 3, right? That's going to be 7. Tell me if I do my math wrong along the way. Then I'm going to do 2 times 0 plus -1 times 5. So that's what, -5? Then we have 2 times 4, that's 8, plus -1, that's going to be 7, right? So here is going to be our resulting matrix. So we know that our matrix products, we know what size it's going to be, because don't forget. So our AB, we have A is going to be a 2 by 2. Our A is a 2 by 2. Our B is what? 2 by 3. So these two numbers inside are the same. So yes, it's defined. Then we know our resulting size matrix is going to be a 2 by 3. So lo and behold, this is a 2 by 3. So what I just did with those numbers, that is the row column expansion. Then when you have the column row expansion, it's going to be a little bit different methodologies. You have these two matrices that are going to result, then you're going to add them up. So 2 plus -9 is going to be -7. Then we got 15. We got 4 plus 3. That's going to give us 7. We got 4 plus 3. That is 7. Then we got -5. 8 minus 1. That's going to be 7. Sorry, so that's going to be our resulting matrices. Once again, this is going to be a resulting 2 by 3 matrices. And lo and behold, those values were the same. So see this matrix that we got by row column expansion? Then here's the matrix we got by column row, but you end up with the same. So you're going to kind of want to figure out what speaks to you. What is something that you think that you can calculate in your head easier?
So you'll be able to choose between row by column and column by row. Question. So you can do either way.
So this is going to be, this one, like I said, the second one I showed you is the column row expansion. Now, once again, I'm going to emphasize order matters, right? You're going to get completely different answers if you do BA, right? You might not even be able to do BA, right? Because if you switch those, then maybe it's not defined anymore. So just be careful of the order. So I'm even going to write it one more time. Order. All right, let's see if we got any questions from online. Online folks, you got any questions? Just want to make sure. Okay. So you guys are doing really, really good. Okay, so we've got, yes, you'll notice that we have matrix forms of linear equations. Like I mentioned before, we're going to see more of that. So you're going to be able, if you see a matrix like this, you might be able to pull out a coefficients. And so you might have a matrix times a column vector, and that is going to give you your B. And so here you would recognize this would follow the suit of AX equals B. So we're going to come back to that. Don't worry about it too much for now. The other thing I wanted to remind you of too is that before we had been working with augmented matrices, that means that we were taking out all the coefficients and including our B. A lot of times they have more sophisticated notation for that, where they'll actually put the line in to show you where the equal sign would go. And then this might be how they write the augmented matrix so that you would realize right away that it's an augmented matrix. So just realize that. Okay, so here we're getting to our transpose. Does anybody want to tell us what's happening in a transpose before I read our definition? What are we doing with a transpose?
Switching the rows and the columns.
Yeah, we're switching the rows and the columns. So that is basically all it boils down to. So if you notice here you have A. In order to turn it into its transpose, you're going to be interchanging those rows and columns. So what's going to happen is if you notice, here's the row A11 and A21. What you'll notice is this number is now going to this spot. So now you'll notice this says 21. Then this A12, it's going to be up here. And then this A22 is going to be in that same spot. So just keep in mind. All right, so what would this transpose look like? So we're going to denote it AT. What would this look like? I'm going to transpose those rows and columns. We're going to start with A11, but what would be the next entry down? Yeah, it'd be A12, A13, A14. Ooh, what's going to be the next top of the column? What's that one going to be? That's going to be A21. Now what? Yeah, A22. This is going to be A23. This will be A24. Then this next one, this is going to now come up here, A31, A32, A33, A34. What do you notice happen?
The size change.
Yeah. So this was a 3x4. What is this one now? This one's now going to be a 4x3. What happens if you have a square matrix? It's going to be the same, right? Nothing's going to happen. So keep all these properties in mind. Okay, so we'll quickly go through these. What are these going to be?
2, 3.
Yep. 5, 6. So this changed from a 3x2 to a 2x3. What's going to happen with this one?
3, 5.
Yeah, so 1, 3, 5. So this changed from a row vector to a column vector. This one stays the same, obviously. Okay. All right. Another one we've got here, a trace of A. So here's the notation. It's denoted by this right here. Whoop, let me check online. Yes, good job. We've got some people putting in the answers there about matrices size changes. So we're going to say trace of A, abbreviated like that. That is going to be the sum of the entries on the main diagonal of A. The trace of A is undefined if A is not a square matrix, right? Why would it be undefined? If it's not a square matrix. Yeah, because if it's not a square matrix, it's not going to have a main diagonal, right? You can only have that if you have a square matrix here. So this one's simple enough. So if you were going to do the trace of A for this first one, what would that equal? Yep, you got it. All this super simple so far. So this would be your main diagonal. Then the sum of those entries, that's going to be your trace. What is going to be the trace of B here? Okay, we've got -1 plus 5 plus 7 plus 0 equals 11. Okay. Anybody? Let me go ahead and see if I can drag this up. Ooh. Come on. All right, well, whatever. So anybody have a cool trick that they happen to know about how to quickly interchange rows and columns if you have a square matrix?
Just change them along the diagonal.
Yeah, what do we call that? So you basically, if you have a square matrix, right? So you know you're going to end up with the same size a matrix if you take the transpose. You can quickly form the transpose if you reflect, if you reflect across this main diagonal. Does anybody know what I mean by that? So here's a quick trick. So you'd be reflecting across that main diagonal. You leave -1 in there. What would be your first reflection?
2 to 3.
Yeah, you got the 2 and the 3 here. Then what would you have? Yeah, you got your 7 and your 1 here. Wait a minute, what? Yeah, so we got the 0 here, then we've got our 4 up here, right? And then we have our -8. What would go here? 2. Okay, then what would go here?
-2.
Okay, we've got -2. And then you've got what? 4. This will be 7, this will be 0, then what do we got? Okay, this will be 1, and then that will be -3. So if it's a square matrix, you can do that quick reflection, if that helps. Otherwise, you can go systematically, down, changing your rows into columns and whatnot.